Hi everyone, I'm going to be going over question number 80 from the chapter 8 bingo problems. Now this problem is really interesting. I drew a little diagram to help kind of figure out what it's talking about. It says that a bullet is shot horizontally at 350 meters per second, and it is contacting this stone that has a mass of 0.1 kilograms, and then that bullet ricochets 90 degrees from its original angle of that it came in with, and its final velocity is 250 meters per second. The bullet mass is 0.006 kilograms or 1 gram. And part A wants to know, it says find the magnitude and direction the stone goes after the collision. So I drew a theta, an angle, and I don't really know which way it's going to go. It's just symbolic, that we're going to find that. So anyway, so the first step we need to do to find the magnitude and direction of the stone is we need to use the conservation of momentum to find the final velocity of the stone. And so to do that, we will say m sub v, which is going to be the mass of the bullet, v initial plus the mass of the stone, times the velocity of the stone initial equals v final plus okay, so here's our problem in an expanded conservation of momentum problem. Now what we need to do is, well, first of all, looking at it, we know that the stone is initially at rest. It's not moving until the bullet strikes. So initially, this velocity is 0, which means we can just cross, that whole part out, which is nice. So then we end up with mv equals mv. Okay. So now what we can do is we can just plug in values for these variables, and this is what we're looking for right here. So when we plug everything in, we get 0.0, we'll just say 6 times 10 to the negative 3 for the mass of the bullet. Times the velocity, which is 350. And that's in the I direction, so we're gonna keep that. And then it's gonna equal the mass of the bullet, which is 6 times 10 to the negative third, times the final velocity of the bullet, which is 250 meters per second in the j direction, plus the mass of the stone, which is 0.1 kilograms, times VSF, which is what we're looking for. So from here we can solve for VSF, and we end up getting that it's going to equal 21 kilograms times meters per second I minus, oops, I need a parenthesis now, 15 kilogram meters per second J. So here's what we end up with for our final velocity of the stone. So now we have this equation. What we need to do though is find the magnitude, right? It wants to know the magnitude and the direction. So we'll do the magnitude first. And we know that the magnitude is equal to the square root of the x, or we could call that I squared plus the j squared. And so when we do that, we'll end up with 21 squared plus 15 squared. And when we do that, we end up that the magnitude is equal to, equals 25.8 meters per second. So that's the magnitude of the stone after it's struck, or after it collides with this bullet. But the question also wants to know the direction. So we know that the direction can be found by the tangent of theta equals, it's going to be the v of the j over the v of x. And so when we plug that in, we know our j and we know our x, so it's going to be tangent of theta equals 15 over 21. So the inverse tangent of 15 over 21 is going to equal our theta, which is that angle. And so that direction ends up being 35.5 degrees. So that's our magnitude and our direction of that stone's movement. So that's it for part A. So I'll erase, we'll keep the information we have, which is good to have. We'll keep these up here, so 25.8. Okay. So now part B wants to know, it says, it just wants to know if that collision was perfectly elastic or not. And so the way we can do that is we know that elastic collisions are equal to, are if the initial kinetic energy is the same as the final kinetic energy. If those two are the same, then we know that it's exactly elastic. If there's any difference, then we know that it's not. So the way that we'll do that is we'll just simply calculate the initial and the final kinetic energies. So we know that Ki equals 1/2 m e v squared plus 1/2 m s v s I squared. And then to plug everything in, we know that it's 6 times 10 to the negative third times that initial velocity is 350 plus 1/2 times the 0.1 times the initial, which is just 0. So this all cancels because that's 0. So we end up with Ki equaling, throw that into your calculator, you get 367.5 joules of energy. So that's our initial energy. So we know that if it's elastic, that the final energy, or kinetic energy, will be the same. If not, then we know it's not perfectly elastic. So put that up there. So now we'll figure out the final. And so that's going to equal, just the same thing. So 1/2 MV VB final squared plus 1/2 MSVS final squared. So now, when we plug that in, we get 1/2 times 6 times 10 3rd times 250 squared plus 1/2 times 0.1 times our magnitude that we found before, 5.8 squared. When we plug that in, we end up getting 220 joules. So that means that some of the energy is being lost throughout this process of this collision. And so since Ki and Kf are not equal, then that means that this was not a perfectly elastic collision. So that's it for part B. Hopefully you learned something. It was an interesting problem to get to solve, but anyway, I hope you learned something, and I'll see you in the next video. Thanks for watching.